You ever wonder how all these complex networks, from your social media feed to the software running on your computer are actually put together? Well, the thing is, they're packed with these hidden, super tight-knit groups. And in this explainer, we're going to break down exactly how we can find them. So, let's just dive right in.
I mean, how do they do it? It kind of seems like magic, right? But the answer, believe it or not, comes from this really powerful idea in graph theory. Think about it. The exact same logic that helps a social network spot your circle of friends is also what helps a compiler make your software run way faster. The secret to both? It's all about finding these hidden groups.
Okay, so here's the game plan. First, we'll talk about the challenge. What are these hidden networks anyway? Then, we'll look at the first fix, Kosaraju's two-pass solution. After that, we'll check out a refinement, Tarjan's super-efficient method. And finally, we'll have a little showdown to see which algorithm really wins.
All right, let's get into it. Section 1, the challenge. Before we start hunting for these hidden networks, we've got to know exactly what it is we're looking for. So what we're hunting for is something called a strongly connected component, or SCC for short. Now think about a network where direction matters, like on Twitter where you follow someone but they don't have to follow you back. An SCC is a special kind of group in that network. It's a group where if you start at any person, you can follow a path of connections and reach every other person in that same group. It's basically a complete, self-contained loop. You can always go forward and you can always find a way back home.
And look, this isn't just some abstract computer science puzzle, right? Finding these SCCs is absolutely critical in the real world. I mean, compilers use this to make your code run faster, operating systems use it to spot those nasty deadlocks where everything freezes up, and of course, social networks use it to find communities and those little friend circles. It's really a fundamental tool for understanding any kind of connected data.
Okay, here's a really important distinction we need to make. In a simple, connected graph, think of it like a two-way street. Direction doesn't matter. As long as there's a road, you're connected. But for a strongly connected graph, it's all one-way streets. Direction is everything. You have to be able to follow the arrows to get from any point to any other point. It's a much stricter, much more powerful kind of connection.
So the big question is, how do we actually find these components? Well, let's start with the first big breakthrough. A really clever two-pass solution called Kosaraju's algorithm.
Kosaraju's method is this neat three-step plan. Step 1, you run a depth-first search, a DFS, on the graph. The key here is you keep track of the order in which you finish exploring from each node. Step 2, you literally create a brand new graph just by reversing the direction of every single arrow. And finally, step 3, you run another DFS, but this time on that new, reversed graph, and you do it in the special finish time order you figured out back in step 1.
Now, that first step, that is the absolute secret sauce here. This whole idea of finish time, where you only add a node to your list after you've explored everywhere you can possibly go from it, that's what makes this whole thing tick. It's like it magically arranges the nodes in just the right order. So when you do that second pass, everything just clicks into place. That ordering is literally the key to the whole algorithm.
So, how does it perform? Well, it's actually really efficient. Its time complexity is O of V plus E. And all that fancy notation means is that its runtime grows in a really predictable way based on the number of nodes, that's V for vertices, and connections, that's E for edges, in your graph. Basically, no nasty surprises. Same goes for the space it needs. It's proportional to the size of the graph.
But there's a catch, and it's a pretty big one. The algorithm has to go through the entire graph twice. You've got one pass to get the finish times, and then a whole second pass on that reverse graph to actually find the groups. Now, that works, for sure, but it does make you wonder, could we do this better? Is there a way to do it all in one go?
Well, the answer to that question is a big yes, and it comes from our next contender, a seriously elegant method from the one and only Robert Tarjan.
So that big question we just asked, can we find all these hidden groups in just a single pass? Tarjan's algorithm answers that with a huge yes. It is specifically designed to find every single SCC by looking at the graph just once. No reversing the graph, no second pass, just one and...
So how on earth does it do that? Well, the core idea is this really clever bit of bookkeeping. It's called the low link value. Basically, as you're exploring the graph, for every single node you visit, you're also keeping track of something. You're tracking the earliest nodes you've discovered so far that you can still get back to from your current spot. It's like you're constantly asking yourself, okay, from where I'm standing, what's the oldest part of my journey that I can still reach?
And here is the magic trigger. This is the whole trick.
During your search, if you stumble upon a node where its discovery time is exactly the same as its low-link value, bam, that's it. That means you can't get back to anything earlier in the search. You've just found the head, the root, of a strongly connected component. And everything you've seen since that root that's still on your current path, all of that belongs to this one group.
And performance-wise, Tarjan's is fantastic. It has that same great O of V plus E time complexity, just like Kosaraju's. But where it really shines is in space complexity, which is just O of V. Why is that better? Well, because it doesn't need to build and store a whole separate reversed copy of the graph, it's way lighter on memory. That's a huge win, especially on top of being a single-pass solution.
All right, we've seen two really powerful ways to tackle this problem. So let's do the showdown. Let's put them head-to-head and see who comes out on top.
So when you put them side by side, the trade-offs become crystal clear. Tarjan is the clear winner on pure efficiency. Just one pass, no need to reverse the graph, it's just better. Time complexity, that's a tie, they're both great. But Kosaraju definitely wins on simplicity. It's just easier to wrap your head around and code up. Tarjan's, with its whole low-link logic and careful stack management, can be a little tricky to get right the first time.
And hey, speaking of getting it right, let's talk about some common mistakes people make. With Kosaraju's, the #1 mistake is messing up that finish time logic. It's got to be perfect. With Tarjan's, it's usually the low-link update logic that trips people up. It's super sensitive. And for both of them, please remember, these only work on directed graphs. Don't even try to use them on an undirected one.
Okay, so let's wrap this all up with the key takeaways. First, SCCs are these awesome, self-contained groups in directed networks where everyone can reach everyone else. Second, Kosaraju's algorithm is your simple, go-to two-pass solution. It's really intuitive. Third, Tarjan's algorithm is the more complex but much more efficient single-pass powerhouse. And finally, the choice between them really just comes down to that classic engineering trade-off. Do you need simplicity or do you need raw performance?
And that brings us to one last question to leave you with. Think about the networks you use every single day. From the web of dependencies in a project at work to the online communities you hang out in. What hidden, strongly connected groups exist there? The next time you're using, well, pretty much anything, take a second and think about the invisible structures underneath that are making it all possible.